light is traveling like this. This is YDSC setup, and these two are slits. What about other maximas? In this YDSC with slab, fringe width will not change. Dear students, welcome to Allen Overseas. Let's continue our special series. This series will cover 45 topics in 45 days. It will be really helpful for all the JEE Main aspirant. This is the distribution of topics in physics, chemistry and mathematics. I'm going to cover physics part. So let's begin with the topic YDSC with parallel glass slab. This topic is from wave optics, and YDSC is very important for JEE Main examination. Before starting YDSC with parallel glass slab, we should know about the optical path length. So what is optical path length? Optical path length in a medium is the corresponding path that light travel in vacuum to undergo the same phase difference. This point you have to keep in your mind. This is very important. So let's understand more about the optical path length. Let's suppose this is the medium, right? And let's say refractive index of this medium is mu, and light is traveling like this. This is the speed of light in vacuum. When light enters into the medium, you know that speed of light will change and it's c by mu, right? Let's say this point is x and this point is x plus delta x, right? So this is the length. This length is delta x. This length I termed as geometrical length. Delta x is our geometrical length, right students? Okay, you know that light is wave. So we can write wave equation. So you know that I'm writing in terms of electric field. So E is equal to E naught sine omega t minus x by v. This is our wave equation, and I'm writing this at this point. So x is equal to itself x. And if I write wave equation for this point, so you can write E is equal to E naught sine omega t minus, this is x plus delta x, right students? So it's x plus delta x divided by v. Okay, you can say, sir, what is this? This is our phase. And what is this? This is the phase, right, for this wave. Is that clear? Let's calculate phase difference first, because same phase difference. So we have to calculate phase difference. So phi 1 I am writing for this one t, sorry, it's omega t minus x by v, and phi 2 is omega t minus x plus delta x divided by v. If you calculate phase difference, so it's phi 1 minus phi 2, right? So phi 1 is omega, I am taking omega common, right students? So omega t minus x by v, right? And minus t minus x plus delta x divided by v. Is that clear students? Let's solve this. So delta phi is equal to, you can see this is t, and when you open this bracket, so t minus x by v, this is minus t, right? And this minus plus, so plus x plus delta x divided by v and multiplied by omega. Okay students, after that you can see here this can you can see here, after that you can see here this cancel, right? And this is minus x by v and this is plus x by v, so this also cancel, right? So this and this also cancel. So delta phi is equal to omega delta x divided by v, right? This is our phase difference. This is the speed of light in the medium. We can write this speed of light v is equal to c by mu. So we have to put the value. So our phase difference is omega delta x and v is c by mu. So delta phi is equal to omega mu times delta x divided by c. So this is our phase difference. Is that clear? In the medium. Let's take air. Just see here. Let's suppose this is air and this is x and this is x plus, let's say, mu times delta x. Mu is any number, let's take. Okay, so you can see here this length is mu times delta x. If you again apply wave equation, so you can see here at x, E is equal to E naught sine omega t minus x by v. No. This is air, or you can consider a vacuum, right? So here speed of light is c. So you have to write x by c. Is that clear? This is at this point. And after that, E is equal to E naught sine omega t minus x plus mu delta x divided by c. Is that clear? This is again phase. This is phase at this point. So if you calculate phase difference again, so you have to subtract this one minus this, right? So omega is common. Again, t minus x by c, right? And minus t, this will become plus. So x plus mu times delta x divided by c. Got it, everyone? You can see here this again, this cancel, this again cancel. So our delta phi is omega and it's mu times delta x divided by c. Just see here, this one, right? And this one. See, we are getting same value. Sir, phase difference is same in air as well as in the medium, right? But in the air, light has to travel how much distance? Mu times delta x. Is that clear? Yes or no? In the medium, it is traveling delta x. For same phase difference, it has to travel mu time delta x. So our optical path length is mu times, you can see this one, mu times delta x, right? Sir, what does it mean? Means if light is traveling delta x distance in the medium, right, for same phase difference in the air or vacuum, it has to travel mu time delta x distance, little bit more than the medium. So this is our optical path length. Now let's see effect of glass slab in the YDSC setup. So you can see here, this is YDSC setup and these two are slits, right? And the distance between the slit is small d, and the distance between the screen at which we will see maximas and minima is capital D, right, students? And there is glass slab, right? You must know, sir, if there is no glass slab, then we know that position of central maxima is at O, right? But there is glass slab, then what will happen with the maximas and minima? Let's understand that. First of all, what we have to do? We have to find out the path difference, okay? So if we calculate path difference, right, this is delta x. You can see here, this light is traveling like this, okay, and wavelength of light is lambda, right, students? So you can see here, they are interfering at this point. This point is O, right, and I am taking position of this point is Y from point O. And at this, I am calculating path difference. So how can we calculate path difference? Path difference is S2P minus S1P, right? S2P minus S1P, right? You can say, sir, here, now light is traveling through the medium. So in that case, what we have to do? We have to modify this S1P, right, in terms of optical path length. We have to first write path length in the air. Okay, so how can we write? Delta x is equal to S2P minus, in air, it's S1P minus T, right, students? So S1P minus T. This is the path length in the air. Sir, what about the medium? So that is optical path length. So that path length, you know that refractive index of glass slab is given, that is mu. So it's mu times T. T is the thickness of glass slab. So plus mu times T. So this is your part difference. When we solve this, so delta x is equal to S2p minus S1p, right, minus t I am taking common, so mu minus 1, right students? If this angle is given, see, this is theta, right? And if we draw perpendicular on this, so you know that this is d sine theta, and you must know in the air S2p minus S1p is d sine theta, right students? So you can write this delta x is equal to d sine theta minus t mu minus 1, right students? Is that clear? You can see here, if we compare d and y, positions of maxima and minima, so d is very greater, large than y. Okay, so with that assumption, you can write delta x is equal to dy upon capital D. You must know this relationship, right? Minus t mu minus 1. So this is our part difference, right? Is that clear? Sir, what about the positions of maxima and minima? So let's see positions of maxima. First is central maxima. So you can see here, this is the screen, right? And these are two slits, okay? And this point is O, right students? And part difference which we are getting, there is slab here, right? Thickness T and mu, this is S1, this is S2, and this is D, right? And this is capital D, right students? So if you see, if you write delta x is small dy upon capital D minus t mu minus 1. This is your delta x. For central maxima, delta x is 0. So you have to put delta x is equal to 0. So dy upon capital D minus t mu minus 1 is equal to 0, right students? So if you calculate y, so dy upon capital D is equal to t mu minus 1, right? So your y is dt divided by small d mu minus 1, right? So you can see here, this is the position of central maxima. Sir, you were saying we will get central maxima in the normal case at the O. But here we are getting some value of y. So that means central maxima is not at this position. It shifts, okay? It shifts somewhere here. And that shift is dt divided by small d mu minus 1. This is the shift. So this is the position of central maxima. Is that clear, everyone? Yes or no? You can say, sir, what about other maximas? So let's find out other maxima. So you can see here, we have to find nth maxima. So to find nth maxima, first write delta x. Delta x is dy upon capital D minus t times mu minus 1. And for nth maxima, your part difference should be equal to n times lambda, right students? So dy upon capital D minus t times mu minus 1 is equal to n lambda, right? If you find y, so you can see here, this is dy upon capital D is equal to n lambda plus t mu minus 1, right students? You can see here, y is equal to d, so it's n lambda d divided by small d plus, right? This is t, right? So d into t divided by small d mu minus 1, right? This is the position of your nth maxima, right? Is that clear? From O. You can say, sir, in normal case, this was the position of our maxima, nth maxima. But here, this term, you are adding extra. So this is our shift, right? What is this? This is our shift of maxima due to the insertion of glass slab. So your whole pattern will shift. Is that clear? Yes or no? By this value. Okay, so it is only shifting. If you find the position of first maxima, right, If you find position of first maxima, I am writing y1 that one. So you have to put n is equal to 1. So it's lambda d divided by small d, right? Plus dt divided by small d mu minus 1. Right, students? This is your position of first maxima. Then position of second maxima, n is equal to 2. So lambda d upon small d plus dt divided by small d mu minus 1. Right? You can see here, if you see here, this term is extra. If you find y2 minus y1, so when you subtract this cancel. 2 minus 1 is 1. So lambda d by small d. So you can say, sir, what you are finding? I am finding fringe width. What is fringe width? The distance between two successive maxima or minima is called fringe width. Right, students? So we already calculated fringe width, and fringe width is represented by beta. Right? Is that clear? Yes or no? And fringe width is lambda d upon small d. You can see here fringe width, sir, we are getting same fringe width as we were getting in that normal YDSC. Yes. So here fringe width is not changing. Always keep in your mind. You can say, sir, what about position of minimas? Now, position of minimas is very simple for you because you have to add only shift. Right, students? So if you write position of minimas, so y is equal to, you must know that is n minus 1 by 2 times beta, and you have to add shift. Is that clear? Yes or no? So y is equal to n minus 1 by 2 beta plus shift is dt divided by small d mu minus 1. So these are the position of your minimas. Is that clear, students? So hope you all understood till here, right? So now let's solve one question based on this concept. So question is, a flint glass and a crown glass are fitted on the two slits of a double slit apparatus. The thickness of strips is 0.40 mm and the separation between the slits is 0.12 centimeter. This is a small d, right? And this is the thickness of the strips. Okay. The refractive index of flint glass and crown glass are 1.62 and 1.52 respectively. For the light of wavelength 480 nanometer. So wavelength of light is given, that is 480 nanometer, right? Which is used in the experiment. The interference is observed on a screen a distance 1 meter away. So capital D is 1 meter, right? So question is, what would be the fringe width? So I think you all know in this YDSC with slab, fringe width will not change. Is that clear? If you write fringe width formula, so fringe width formula is beta is equal to lambda capital D upon small d. This is fringe width formula. We have to put the values. So just see. So beta is equal to lambda. Lambda is wavelength, that is 480 nanometer. Nano means 10 to the power minus 9. Okay. Capital D is 1 meter, right? Divided by small d. Small d is 0.12 centimeter. So let's convert this into meter by multiplying minus 2. So you can see here, we can remove this 2 zeros. Then this is 40. So 40 into 10 raised to the power, this is minus 7 because these are 2. So minus 7 and this is plus 2, right? So beta is equal to 40 into 10 raised to the power minus the 7, minus 7 plus 2 is minus 5. So beta is equal to, we can write 4 into 10 raised to the power minus 4 meter. Is that clear? So this is the answer for the fringe width, right? Next question, at what distance from the geometrical center will the central maximum be located? Okay, now see. So in our setup, two slabs, they are using two slabs, okay? And this is the screen and wavelength is given 480 nanometer and thickness of slab is given 0.4 millimeter, right? And separation between slit S1 and S2 is given 0.12 centimeter, right, students? And this is 1 meter. You must know, if I talk about the central maxima in the normal case without any slab, so it lie at this position, right? Is that clear? But there are two glass slab. So we have to find position of central maxima, so it will shift. So we have to find shift in the central maxima by this slab and by this slab, and after that we have to find net shift. Is that clear? So you must know the formula for shift. So I am giving the name y1, so that formula is dt divided by small d into mu1 minus 1. Refractive index of this is mu1, that is 1.62, and refractive index of this is mu2, that is 1.52. Right, students? So we have to put the values. So y1, sorry, I am not putting the value. Then we have to find shift because of this also. Is that clear? So y2 is equal to dt divided by small d mu2 minus 1. Right, students? Then we have to find net shift. So net shift in the position of central maxima is y1 minus y2. Right, students? Okay. So y1 is dt minus d. When you solve this, you will get mu1 minus mu2. Right, students? After that, d. Capital D is 1 and thickness of slab is 0.4 mm. So it's 10 to the power minus 3. Capital D is 0.12. Right? It's in centimeters. So 10 raised to the power minus 2. Mu1 is 1.62. Mu2 is 1.52. Let's solve this. So you can see here 0.4 and this is 0.12. So this is 0.3 times. Right, students? And this is minus 3, this is minus 2. So you can write 10 raised to the power minus 1. This is 0.3. So I am writing this. I am removing this point and increasing 1 0. So here 0. Is that clear, everyone? After that, 1.62 minus 1.52 is 0.1. Is that clear, everyone? So you can see here, this is 0.1, this is 10 to the power minus 1 and this is 10. So you can write this 10 raised to the power minus 2 plus 1 divided by 3. Is that clear? So just see, it's 10 raised to the power minus 1 divided by 3. This is in meter. Is that clear? If you want to write your answer in millimeter, then you have to multiply with 10 to the power 3. So it's 10 to the power minus 1 multiplied by 10 to the power 3 divided by 3 is equal to 100 by 3 millimeter. So this is the answer for this question. This is the position of central maxima because of these two slabs. Is that clear? So that's all from my side on this topic. Don't forget to watch complete series. The playlist link is available in the description box. Still, if you have any queries or suggestion, feel free to reach out to us in the comment box. For more, stay tuned with us. Thank you.